Okay, so here we go. So what we're going to have to do is we're going to have to draw these Lewis structures. Now, I'm going to zoom in and I'm going to kind of make them really tiny just to make sure they make sense. Now, I've actually drawn I3 minus for you guys a lot. And so I'm just going to draw it one more time. And like I said, it's going to be really tiny when I back this thing back out. But you got to remember that if it's charged, it's always got to be in what? It's always got to be in brackets. And remember, I3 minus... And I know that's really hard to see, but it's 3 I's with 3 valence electrons, or 3 lone pair around the central molecule. Now, this one is, I'm going to go ahead and tell you, this is linear. And this was the actual Lewis structure they had to draw back in 2012. So I highly doubt you're going to see this one again. Okay, guys, you have it a little easier than I do. What is the next Lewis structure? What's the next formula? SF5 plus. All right, so we need to kind of calculate this because I don't know exactly what it's going to look like. All right, so I have S, I have F. So it's 1 times 6, and it is 5 times 7. So 35 plus 6 is 41. But you got to account for this plus. What do you do when it's plus? Subtract 1. Which gets me back down to my even number. Okay? So now I know that I've got to do brackets. I'm going to go ahead and start like this. 1, 2, 3, 4, and 5. I may have to change it. F, 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 F. All right, so how many have I used of my 40? All right, so how many do I have left? Thank you. I've got 30. And then each F gets 6, right? So how many Fs do I have? 5. Well, how many is 5 times 6? 30. So doesn't that mean I'm out? Well, there's my shape. On May 4th, on Monday, what are you going to do? No. You'll actually draw. You'll actually put the dots, right? Oh, very good. Thank you. And the plus. I think he's still here, Matt. Chair, I think he's still here. But it'll be okay for right now. Okay? All right. This shape, I'm going to be honest with you. I'm not quite sure what the shape is. It's AB5. I think it's trigonal bipyramidal. Okay? And so we'll just kind of go from there. All right. What is the next Lewis, or what's the next formula? SF5 1 minus. Now, should we really even have to think about how to do this one? What's the only difference? I add, and I'm going to be honest, I'm not quite sure how to draw this one, so I'm going to draw it. Yeah. But let's just be honest. If it's 1, 2.
Why not just do it like all in the bottom half and then draw the bit of what's
You could. 2, 3. 5. Be like that. It doesn't matter. As long as you have 1 valence pair around the central molecule, it's okay. And it is 1 minus. There is a difference in the hybridization. Do you agree? What do you do for hybridization? Put the petals, right? So what would put them around everything? So it's S, P. All right, so S is the electrons, P1, P2, P3, and then D2. And I'm going to go back over and go ahead and do the hybridization for this one. It's S, P, so S is that one, P1, P2, P3, and then it's just D1, so SP3D. Does that make sense? All right, how many more Lewis structures are there? All right, so TeCl3 positive. Te, I have no idea what group. I know, but I don't know what group it's in. But say, you tell me, Jonathan.
It's number 43. It's atomic mass is 98.
I need the group number.
It's in the transition metals.
No, it's not.
TE. Oh, that's TC. That looks a lot like an E. Oh, it's in So you're 2, 5, 6, 6.
Thank you. All right, so 21 plus 6 is 27. And what do I do with that 1 plus? Subtract an electron, so that gets me down to 26. I know it's a plus. All right, I'm just going to go ahead and draw it like this. I may be right, I may be wrong. Cl, Cl, Cl. All right, so how many bonds have I used, or how many have I used in my 26? All right, so 26 minus 6 gives me 20. Each, what are those things? Outer atoms, yeah. Gets how many? 6. 6 times 3 is 18, so how many do I have left? Where's it going to go? On top. What shape is that? Trigonal? Pyramidal. Okay? Because if you think about it, really, I should have done this. Ooh, it erases good. Sometimes whenever you start writing this, the erasability goes away. So really, it should be kind of bent down like this. Now, obviously, on May 4th, you're going to write the dots around it. Put all 6 dots around it, okay? Now, hybridization. S takes care of that. P1, P2, P3. So sp3. Everybody good? All right. And then what's the last one? XeF3 minus. So Xe is 7. F is 3 times 7. So 21 plus 7 is 28. Whoa, why did I say, yeah, that's wrong. It's not 7, it's what? It's 8. All right, so this is 21 plus 8 is 29. What do I do with that one less charge, that one other charge? I add a negative, so it's 30, which gives me a negative out here. And so I'm just going to draw it like this. May need it, may not need it. All right, so out of my 30, I've used how many? Minus 6, that gives me 24. Every F gets how many? 6, so 6 times 3 is 18. So how many do I have left? Ooh. Is that right? It could have an expanded octet, but I didn't think it'd have 3 lone pairs.
Could you double bond?
No. So it's got 3 lone pairs.
You can't double bond.
Why would you double bond fluorine? You don't need to.
Well, why have I?
That's weird. Parker, you like to do this. Look up AB3E3. I don't even know if that's real.
Alright.
But anyways, we got that. All right, so now when I back out,
Is that right?
yeah, it has to be right. 8 times, all right, 3 times 7 is 21, right? 21 plus 8 is 29. Plus 1 is 20, plus 1 is 30. All right, I use 2, 4, 6. 30 minus 6 is 24. 24 minus 18 is 6. It has to be right.
What would that be called?
That's what he's looking up.
Is that how you would write it too?
It's got 3 lone pair around the center. It's good for me. T-shaped? AB3E3? T-shaped?
T-shaped must cover a broad spectrum because I think we've seen that before.
Yeah.
But with the difference
All right. Which one of these has an sp3 hybridization? That was easy.
I can airdrop it to you.
No, I'm good. Which one's sp3? It's D. Which one has sp3d2 hybridization with 1 unbonded pair? That's SF5 1-, right? That's C. Does that make sense? Is it helping seeing these Lewis structures being drawn? Okay. Which one has a D sp3? It's kind of weird. And with a bond angle of 120. It's just backwards from it's backwards from how we wrote it. Yeah. Which one is it? It's the SF51+. Remember how we did the hybridization? Do I need to zoom in and show you? Remember right there? sp3d. And it's just got one of those funky angles. And then, all right. Ooh. Oh, okay. And let's go back and let's look at this one. Let's look at the hybridization of this one because we didn't do the hybridization. So I've got S takes care of that one, P1, P2, P3, and then D at the top, right? So they both have sp3ds. But what have I told you about I3 minus? It's what? It's linear, right? Which is 180 degrees. So that would give me A. And then is a symmetrical species with unbonded pairs on the central atom. What's the only one that's symmetrical? It is A. Very good. Yes, sir. All right. These questions are real good. These are part B. This is the second part of quiz number 16. This graph would be used to determine the activation energy of a reaction. If you missed this one, you are just plain out dumb. I'm being honest. What is it? Seriously, guys?
It's definitely E. There's like no other choice.
All right. 7. Hold on, I'm going to come back to that. 7. This graph will be used to show that the reactant is 0 order. Remember, we have cleaner graphs, right? Which one was 0 order? C, which is the concentration versus time. So what would it be? It would be C. All right, this graph would be used to show the reactant is first order. What is first order? The natural log, which is what? E. Very good. Be very careful because there's a difference here. 9. This graph will be used to show that a reactant is second order. It is D. Very good because it's the reciprocal. This graph will be used to determine the half-life of a radioactive isotope. Oh, okay, that makes sense. Remember when we talked about half-lives? If it's a half-life, oops, that's wrong. If it's a half-life, it has to be first order. I'd make that little note. Well, that's easy to tell. Which one is it then?
E.
It is E. Very good.
Wait, what was the formula for half-life again? It was like
That's actually a good question. It is T1/2 equals 0.693 over baby K.
Is that going to be on the...
That is on the formula sheet. That is on the formula sheet. Okay.
Clarify, what was C again? Clarify.
Say it again.
C was A, right?
C was A.
I mean, 6.
6. You know, they got me on this one. I looked down and the answer is not what I thought it was.
6?
It's not A, is it?
It's not A.
I'm guessing
It is B. Here's what this is right here. And I want you to write this beside this. This right here is Maxwell Boltzmann.
Oh, yeah. But is this like, that's basically T,
And what this is, remember, this is the number.
so is this
Like
like,
the higher temperature is like the
Yeah.
lower one.
So this is activation energy. Remember, the higher the temperature, the shorter the hill gets. But what happens? You have a greater area beyond the activation energy line, which means you have a better reaction. That's what Maxwell Boltzmann is.
So how they answer that? Like, how do you ask that question?
it's part of,
Like, which one's Maxwell Bolton?
Yeah. Which one represents the A? All right. So a question for A would be, which graph represents a reaction that has a change or a higher rate of reaction? More collisions equals a faster rate. So when you change the temperature, you have so when you go from here to here, the rate must increase because you have more collisions. Okay. Now, I'm going to be honest with you. It says that B is the answer for determining the activation energy. So I apologize and I retract the statement of if you missed this one, you are dumb. Because I'm dumb because I don't know how they got this answer. I'm 100% honest with you. Can anybody give me a guesstimation why? B?
it has something to do with gravity. Because it has temperature. If it's like,
Not true.
that's log K.
Mhm.
Inverse.
I should have been keeping up a long time ago. Be way lower. Okay. Yeah, y'all got me on this one. Okay, next slide. All right. Here's the great news. You can completely cross off 1 through 5. The reason why is because this is nuclear chemistry, and nuclear is not going to be asked on the exam. These are actually a little bit easier to do. These Lewis structures. Let's actually run through those real fast. All right. What is the first one? CBr4, right? CBr4. All right. What do we know about carbon? It's always in the middle, right? It is a tetrahedral. That one should be really simple for you to do. All right. What is first? So that is tetra, polar, nonpolar. Nonpolar bond angle, 109.5. Since it's non, it's also what? LDF. Hybridization, sp3. Okay, we're good on that one. What's the next one? PCl5. Now, what looks weird about P right here? It's going to have an expanded octet. Remember? Do y'all remember that little phrase that I gave y'all about the periodic table and what's it can have expanded octets and which one can't?
It's that.
Peter sips chlorine
Oh, wow.
as Selena breaks crayons telepathically in X-Men.
No.
If you look on the periodic table, start with Peter is
You just
phosphorus.
made that up by yourself.
Actually, Honors made it up this year.
That's scary. Why would anybody? Yeah, why would you let Honor do that?
Y'all made stuff up.
That's like too long.
Peter sips chlorine. That's phosphorus, sulfur, chlorine.
It sounds like
As Selena breaks, as Selena breaks crayons. Arsenic, as selenium, bromine, crayons is krypton. Telepathically in X-Men. Tellurium, iodine, and xenon. So it's just how it flows. Okay?
We also changed it up the way it goes.
Yeah, I've changed that up a little bit too. Limiting reactant. All right, so we've got this structure right here. Now, this one's a little weird. Parker, you just looked this up. This was AB5. This is trigonal bipyramidal. But what's your, the bond angle is weird. It's 120 and 90. Polarity. Very good, Matt. It is polar. The reason why is because nothing is symmetrical. There's an oddball, right? Is the top symmetrical? Yes. But are the sides symmetrical? No. So you're going to have a difference of electronegativity there.
It would look.
Kinda. That's you could actually draw it. You could actually draw it like this. I would kind of draw it like you know what I'm saying when I say the Chrysler symbol?
Yeah.
Kind of like that. That's probably the most accurate way to draw it. I just kind of turned it on its side. No. Ooh.
That's what I'm saying.
Yeah.
I mean, if you drew it at the slant angle.
Yep. All right. Also, hybridization. SP, that's S, P1, P2, P3. So sp3d. Okay. All right. What's the other molecules? Yeah. What's the next one?
PCl3.
PCl3. Oh, this one is, I actually have to calculate this one out. 5 times 1, Cl is 3 times 7. 21 plus 5 is 26. I think there's a lone pair on this one. 2, 4, 6 leaves me with 20. Yep, there's a lone pair. All right. Every chlorine gets 6, right? How many chlorines are there? 3. So 3 times 6 is 18. So minus 18 leaves me 2. So there is a lone pair on phosphorus. Shape. Very good. This is pyramidal or pyramidal. Bond angle. 107. Polar, nonpolar. IMF. Which one is it not?
That one, it's not LDF.
You know it's not LDF because it's polar, and you know it's not hydrogen bonding because there's no hydrogen. So it automatically makes it dipole-dipole. What is
Right through
this?
middle. There's your molecule.
Little balloons.
I don't like
You don't like
That way you
balloons?
can see the bond angle 90.
I just don't like balloons, and so I've never done it with balloons.
But do they actually make that little, that's.
Yes, that's actually how the molecular orbital structure
Like,
looks.
they make one with like 20 insert slots for like the method you use.
All right, let's see. This is
You're not looking at the atoms, you're looking at the orbitals
yeah.
here.
It's how it actually like expands out. It's not. Remember, it's 3-dimensional, right?
Yeah, but it wouldn't be like, rotated 90 degrees.
Yeah, this is tetrahedral.
Green and yellow, top and bottom, pink in the middle.
Yeah.
Here's your, yeah, up in the middle.
Well, this is tetra.
Yeah, that would be tetra. But you can see the pink ones are at the 120 degree angle from pink to pink to pink. They're at 90 from pink to yellow, or pink to green.
If there was another, imagine another one sticking out right here.
Right, yeah, then it'd be like a window logo.
Right, there you go.
All right, hybridization. So that's S, P1, P2, P3. So sp3. All right, is there another one to draw?
SO3.
All right, yeah, let's actually do that one. Yeah, I think this one has, I think this is a double bond. I'm not sure. Sometimes you just got to draw them out. All right, 18 plus, or that's just what, 24? All right, 2, 4, 6. Oh, no, I'm good there.
Nope.
Yeah. 2, 4, 6. 24 minus 6 is 18. And then, okay, actually, this was going to turn out to be a little better. Let's erase this. There's no lone pair. It is planar. Very good. So you have 120. Hybridization. SP2. Polar or non-polar. As soon as you say non, what else is the next thing you write? Got to write LDF. Okay? Everybody good there? All right, so now let's actually look at the questions, now that I've drawn all those. All right, which one of these has a square planar geometry? That's the only one that we didn't label a shape on. What? Oh, I didn't draw XEF4. That would help, because I think that's actually the answer.
Because of the two on here.
Yeah. XEF4. XE is 8. F is 4 times 7. 28 plus 8 is 36. Okay, 36 minus 8 is 28. All right, so how many is each F going to get? So 6 times 4 is 24. What do I have left? I've got, why not write 2? I was thinking 2 lone pairs. So I've got one there, and I've got one there. This is square planar. Okay, so an AB4E2 molecule is square planar. All right, so now, oh, whoa, whoa. I can't get, oh, that sucks. Wow. All right, so let's try to answer it. Now we know which one has a square planar, that is E. Which one's tetrahedral? The first one, A. Which one has an unbonded pair of electrons on the central atom with an sp3 hybridization?
Oh, that one right there.
Which is what?
Right there.
PCl3, which is C. Wow, this is rough. It has an sp3d2.
Yeah.
No, it's not. It is. Why did I count that wrong earlier? Because I have it as sp3d. So S P1, P2, P3, D.
Okay, so it's not that.
Would it be E?
So wouldn't it be,
Oh, it's the, no, yeah, it is E, dust. It's in this big bold thing that won't go away. So we've got S, P1, P2, P3, D1, D2. Okay, so it is, whoa. It is E again. And then has a trigonal planar. Trigonal planar is SO3, which is D. All right, that slide's way messed up. Oh, what? Did you see that?
and you just shrink it away.
We got it, let's go on.
We'll shrink it into solid points. Guys, coming tomorrow.
Okay, all right, next slide. All right. It is a halogen. Wow, they got real easy real fast, didn't it? Is an alkaline earth. What's sad is some of you, or some, not of you, but some people would miss this. That would be B. Is a liquid.
That'd be D.
D. The last stable element. Well, I have no idea, but I know that C is uranium, and it is bismuth. E is the last stable.
Think about that pink stuff you.
Last.
Pepto. That's pretty standard, you know, Justin.
Or you can drink the
When did,
the white chalky powder stuff. Totally just barium something. Barium sulfate.
Yeah, barium, magnesium, something.
Yep.
Milk and magnesium.
All right. So now that we understand this, it consists of all sigma bonds. Now, what did we just say? So I'm just going to kind of recreate this. So it's kind of in my terms. We know that HH is a single bond, right? Well, it's kind of what he just said. So if it's a single bond and it's on the plane, that is a sigma bond, right? And it's kind of done like this. It's a lowercase, funky looking thing. That's a terrible job. Sigma. But we also said, O creates a double bond, right? But what do we know about those? It's kind of the way he just explained it. Since it's a double bond, is it on the plane? No, it's going to kind of wrap. So let me change colors. It's going to kind of wrap around like this, right? It's going to wrap around like that. And the final one is N, and we know that it triple bonds. We just talked about this. Well, if it's a triple bond, the O, not the O. Yeah. Come on. The N is going to be bonded on the plane with the other N, and then it's going to be looped and looped, which is going to actually pull these two things closer, which we already know is true. Now, the good news about these molecule structures, we've already drawn them. Which of them consist of all sigma? So what's another way of saying that? All single, and has planar geometry. That was the one that was trigonal planar, right? So it's kind of the same concept. SO3, which is D. Requires resonance structures to describe the bonding satisfactory. Now, what is resonance?
Same molecule, different shape.
Yeah, same molecule, different shape. Was there any of those that could have had a resonance?
PCO5, PCO3.
I don't remember any of those having resonance.
You find more resonance with your,
Expanded octets?
yeah, expanded octets and also the organic chemistries.
Yeah, definitely organic. Is it this one?
So, we know we can, hope so. Just release this
I didn't say Mr. Bilal couldn't be in the room.
Touche.
Just doodle on the board.
I don't know if it's this one. I don't know if it's this one or not. I have the answers right here. Is this number?
Oh, by the way,
It's A.
Hey, you.
Tetrahedral?
yeah, you sitting at the two.
Yeah, that's strange.
Do you understand that one? Why tetrahedral would need resonance? I'm not sure about that one. Has only one unbonded pair of electrons on the central. We know that one. That one was C. has an sp3 dehybridization. Which one was that one? I don't remember the
That was B.
Was it B? Okay. And then it's a polar molecule.
That'd be B.
That was C. No,
Yeah, it has only one unbonded pair, so we can make it C.
it says it's D. That makes no sense at all. No, I'm looking at the wrong one. My bad. It is C. Sorry.
Yeah, because it says it has one.
Yeah, let me double check.
Just read the previous.
Hey, are we on 18?
Yeah.
Yeah, we're on 18. It is the first answer choice is E, which is the one I just drew down here. Okay, this does make more sense now, because what you can do is you can draw it like this. Because if you draw it like this, it becomes polar. If you draw it where the red X's are or the red dots are, it's nonpolar.
So the same molecule can be polar and non-polar
Depending on the placement of the electrons.
So you can literally twist the molecule.
And notice what it says. It says requires resonance structure to describe the bond satisfactory.
It wants to be the one on the left, but it can be the one on the right.
Exactly. Depending on how the electrons displace itself around the atom.
Because the one on the right can bond easier to another compound or molecule than it can
So
the
it's
one on
like
the
it
left.
would, it's like a top would shift and then the other one would pull up and shift. Or
Yep.
however.
It's different. It's how you place those electrons around the molecule.
That's cool and unusual.
Do you see why the one on the right would bond more easily to another atom or molecule than the one on the left?
Because you got these things out here
See,
floating around.
fluorine itself has electrons on the outside pushing away.
Here's some things that are real life applications. One, utilized as a coating to protect iron from corrosion. Lead, calcium, zinc, arsenic, sodium. I would hope it's not sodium or calcium. Why? If you throw those in water, good luck. Galvanized. Is that where they're going with this? That's okay.
Zinc oxide. 'Cause
That-
it takes so long to oxidize, and once it does, it's not going to oxidize further. You ever got one of those iced honey buns? Okay. What
Guys, y'all
makes
listen.
icing white is zinc oxide. It's zinc rust. That's what makes your icing on pastries white.
Delicious, we're eating rust.
Let's actually look at 3 real quick, because I think you should get this. Utilized as a shield, a source of radiation. So when you go get an X-ray done, what do they put on top of you? A lead vest. So that's going to be A. Used in light bulbs to produce a yellowish orange light to control light population. What did I say?
Population.
Did I really?
Guys, why is
Go
lead,
home.
Why is lead used for radiation blockage? It's the densest, most stable element. In fact, all the radioactive elements decay down to lead.
Like we went to.
It's the most stable, densest, I think.
Yes.
No, osmium is the most dense for sure.
Is it? 'Cause
It
that's
is for
not how
sure.
I was taught.
No, it is. I've got a periodic table. It is the
Wow.
most
It's
dense.
changed since my last periodic table was 6 years old.
All right. Used as poisons for rodents. That's definitely jumping out at you, right? Now the other one is added to silicon to enhance its properties as a semiconductor. It's calcium. Now, you have an answer for that one? Why calcium's added to silicon?
Calcium's a true metal.
Calcium group
Yeah.
and silicon the group 15.
No, 14. It's that's because those silicon-based life forms. It's just like carbon. If that makes sense.
The same thing that a circuit board's made of is that window behind the silicon.
So it's another form of a basic glass. Here's some good ones. These are some definitions. Can be used to predict that gaseous carbon atom is in its ground state is paramagnetic. Ooh. What is paramagnetic? Remember, paramagnetic means that it has the ability to have another pair to be made. Because carbon, remember, is 2p2, right? All right, yeah. So it's just like this. because it's specifically carbon. So it needs another electron to become diamagnetic, correct? Whose thing did we use to talk about how you fill electron orbitals?
Frames per second. When they slow down the laser beam going through a coke bottle, the light is affected.
Oh, I actually fixed it. All right, it can be used to explain the ionization energy trend going down a group. What is an ionization energy trend? That's how much energy is required to remove an electron, right? Okay, think about this. If I'm dealing with lithium, do you agree I have 2 electrons in the first shell and then 1 in the outer shell? Okay, what is holding that electron out here in the valence shell? What's holding it on? Isn't Zeph holding it on? Does that make sense? What happens when I go down? What's the next one? What's after lithium? Sodium? Am I right? All right, so I've got 2 electrons, and then I've got 8, and then I've got 1. Did it just get harder or did it just get easier? It's got harder, right? Well, what happens when I go down to potassium? When I've got K, I've got 2, I've got 8, I've got 8, and then I've got 1. So every single time, we're adding another orbital, which making it harder and harder and harder to hold on to that energy, right? So as I go down a group, what is happening to my ionization energy? Is it requiring more or less energy? Less energy, right? Well, what are those other orbitals doing from the nucleus to the valence electron? It's shielding it. That's what the shielding effect is. Basically, if you were trying to get to the front of the line of the lunchroom, what's gonna be in your way? Other people. They're shielding you from the front line. So think about it. If I need some chicken nuggets, there's someone in my way. They're shielding me from those chicken nuggets, right?
I know, right?
I walk up in front of everybody. That doesn't matter. Okay?
Think about the teacher in the front of
All right, number 1. This is quiz 20. A precipitation reaction. Dear Lord, please tell me you get this one right. Of course, Teresa. Okay, it is D because it's the only solid being formed. A reaction that produces a coordination complex. Guys, complex means weird and strange. What up there looks like a product that is weird and strange? You want to try E?
Platinum? That doesn't seem too strange.
Look at that thing again. That is PTCl6 2 negative. That's a little weird and strange, isn't it? Okay. Really, the word they left off that they should have included, but it would have thrown it off or thrown it away, was ion, because it's really a coordination complex ion is what it's really called. So they've left that word out. A reaction in which the same reaction undergoes both oxidation and reduction. Ooh, that's a good one. I actually have to think about this one for a second. It is C, and here's the reason why it's C. All right, remember, when you're doing oxidation numbers, let me kind of zoom in on this. When you're doing oxidation numbers, remember the easy part is to do it twice or find the zeros first. So if you look at it from here, do you agree that bromine is a 0? And then what is it right here? It's -1. But if you do this, it's -1, -2, -6. So what does that make bromine? +5, right? So bromine actually went to -1 and it went to +5. So it went up and down. Does that make sense? All right, so the trick is, the way to look at this is the one element has to be on the same side twice. Well, if you look at B, is S or O on the same side twice? Nope, well, B's out. Whoa. All right, look at D. Is calcium or sulfate on the same side twice? Nope, neither is the last one. And then, no, oh, it is. Okay, I didn't even see that. My bad. So that throws that one back in. But notice, right here, it's -1. Here it's -1, and there it's -1. So they're all going to be -1s. And then H is on the top as well, but we're not going to go through those. Oh, no. Okay, what about 4? A combustion reaction. Sorry, not mixed. What does combustion have to have? It's got to have O2, so what's that make the answer automatically? It's automatically B. Guys, combustion does not have to be a hydrocarbon. Does not have to be. All right, a reaction that shows a Lewis acid base. Guys, cross it off. You will not have to do that on the AP exam. All right, last step. We're done after this. Okay. What is the most electronegative element above? It is oxygen, so say. Which element exhibits the greatest number of different oxidation states? Well, we can automatically cross off B, C, and D because all metals, their charge are their oxidation states. And that is a group 1, that's a group 1, and that's a group 2, so they're not going to change. But nitrogen and oxygen do have the ability to change, and I'm going to be honest with you. What, are we on 20 still? All right, answer is E, nitrogen. I know this, that oxygen only has a +1. It has a -2. Sorry. All right. I know oxygen's oxidation states are -1, -2, and +1. I know those for a fact. 5 negative, or excuse me, 3 negative, +5. There's another one. I can't remember what it is, but it's got more. Yep. All right. Which of the element above has the smallest ionic radius and is most commonly found ion? Which one of these has the least number of electrons? Hold on. It says D. That doesn't make any sense. Which of the following has the smallest ionic?
Oh, yeah, because it goes down, but it's the
Top. All right. Used in fireworks to produce a red color. You will not have to know that. They're not going to ask you anything about color. But it is B. Strontium is the red firework color. And the last one, which of the elements above has the largest ionic radius and the most commonly found ion? Now, how can you say that? How can you say the smallest ionic for its most commonly found? That doesn't make any sense at all.
Is it C?
It's E. I don't get 8 or 10. All right, guys, we're done.